Hi, it's me again, Tammy Lester-Claire. In this final mini lecture on XRF, I'm going to talk about some of the nuances to interpreting XRF spectra. While XRF spectra can look simple, and with the use of an emission peak table, assignments can be easily made, it is also easy to make incorrect peak assignments and identify elements that are not present, or to miss elements that are present. Here's a process to avoid mistakes. So 1, know the instrumental conditions used to collect your spectrum. Know the type of metal target, the tube voltage, whether a filter was used, and what the detector type was. Characteristic lines from the X-ray metal target will nearly always be present in your spectrum. So don't use an X-ray tube target of the same element that you want to detect. And know that the presence of those lines is due to the target itself and not necessarily your sample. Know the tube voltage setting that was used to collect the spectrum. All peaks that you observe in the spectrum will have an energy lower than the maximum tube voltage setting. If you use a metal filter, like the metal target, those lines will show up in your spectrum. Your detector type will also determine the resolution, the emission line energies that can be differentiated from each other. And also, some detectors produce artifacts in the spectrum. More about that later. Step 2, identify every peak present in your spectrum. Everything should make sense. There should not be any missing emission lines. Any unexpected peaks need to be identified. Step 3. Most elements will have more than one emission line visible in the spectrum. Those are lines such as the K-beta lines. Those other lines, such as the K-beta lines, should be observable. If not, then the K-alpha line may not be what you thought it was. So be aware of the following in interpreting XRF spectra. 1, look for overlapping peaks. Those would arise from two lines being in the same position, which is to say they have the same energy. 2, look for some peaks. Those occur when two photons enter the detector at the same time. 3, you might see escape peaks. The detector material, silicon, absorbs some of the energy from the incoming photon and produces peaks having different energies than those expected. And 4, look for blank peaks arising from trace contaminants. So now we're going to talk about each of these 4 possibilities individually. So overlapping peaks. While the K-alpha peak for each element occurs at different energies, as does the K-beta peak and the K-alpha, and all other peaks in the XRF spectra, in some instances, energies from two different lines from two different elements are the same. For example, arsenic's K-beta peak is nearly identical in energy to Mercury's L-beta peak. Actually, the two emission lines are not the same. Their energies do differ by 0.09 keV. But remember that the resolution of an SDD detector is 0.12 keV. So the detector cannot distinguish those two energies from each other. Before SDD detectors came into widespread use in portable XRF instruments in around 2008, the resolution of detectors in earlier instruments was about 40% poorer. A clue that both emission lines are in fact present comes from the fact that the K-beta peak intensity is much lower than the K-alpha peaks. But having these two lines occur in the same place makes this peak look larger than would be expected for a K beta peak from either one of these elements if they hadn't occurred together. Well, SDD detectors can count incoming X-rays very fast, remember in approximately a millionth of a second, depending on the X-ray tube and current. The instrument may be emitting X-rays faster than they can be counted by the detector. So some peaks arise when two X-rays hit the detector in the same millionth of a second time frame, which causes the detector to respond as if a single X-ray having an energy equal to the sum of the individual X-rays hit it. In this figure at the top, you can see that two copper K alpha X-rays hit the detector at the same time. The detector responds as if a single X-ray photon having an energy of twice that, which would be 16.10 keV, hit it instead of two X-rays with half that energy each. The bottom figure shows a spectrum with multiple sum peaks visible in the black text. And so you can see the chromium K alpha plus chromium K alpha sum peak here, and chromium K alpha plus chromium K beta sum peak, and so on. And so I've provided an abbreviated emission line table over here to allow you to identify all of the sum peaks that are present. Three, escape peaks are caused when an incoming X-ray's energy is absorbed by the detector material, which is silicon. Silicon's K alpha peak energy is 1.74 keV. So, in effect, the detector's response to the incoming X-ray is reduced by that amount. Here, we can see that an incoming X-ray, a copper K alpha X-ray having an energy of 8.05 keV, is actually measured as having an energy 1.74 keV less than that. So 8.05 minus 1.74 gives us a peak energy of 6.31. So the detector produces a response to the system, to the transducer, which then goes to the signal processor and readout, showing an escape peak having an energy of 6.31 keV. Escape peaks can be easily recognized in a spectrum because their energy is 1.74 keV less than other elements that are present in the spectrum. So here we can see three escape peaks shown. They're the result of titanium's K alpha and K beta, as well as copper's K alpha peak. You will most often observe escape peaks when the energy of an incoming X-ray is close to that of silicon's absorption energy, so in the lower keV range. Four, blank peaks. If you collect an XRF spectrum of air, you will see a number of peaks from different components of the instrument. Of course, instrument manufacturers try to design their instruments to minimize so-called blank peaks. It is good practice to collect a blank spectrum once you have set up your instrument with the filter, tube voltage, and current that you plan to use. It is also possible to subtract the blank spectrum from your actual spectrum. There are some corrections that need to be made to do that correctly, such as normalizing the spectra to the Compton peak, but let's save that for another lecture. Hopefully you've noticed by now that X-ray emission energies increase with increasing atomic number. In other words, as you move across the periodic table, the energy of the K line, for example, increases. The same trend happens with the L line and the M lines. This figure shows energy lines up to 10 keV for many of the elements. So from those trends that I just showed, we can make some generalizations about which lines are observable using X-ray fluorescence instruments. So generally speaking, organic elements, which is to say hydrogen, carbon, nitrogen, and oxygen, do not give detectable X-ray peaks. This is because the X-ray emissions from these elements are too low in energy to be transmitted through the air and are not efficiently detected using conventional silicon-based detectors. Low Z elements, for example, chlorine, argon, potassium, and calcium, give only K peaks. The L peaks from these elements are too low in energy. These photons are not transmitted through the air and, again, are not detected with conventional silicon-based detectors. High Z elements, such as barium, mercury, lead, and uranium, give only L lines. The K lines from these elements are too high in energy. These electrons have high binding energies and cannot be removed with the limited voltage available in field portable instruments, which can be up to about 50 kiloelectron volts, sometimes only 40 kiloelectron volts. Middle Z elements, rhodium through iodine, give both K and L lines. Bye for now.